Good morning, guys. I realized that the video I posted for whatever reason did not record my sound, so I'm just going to record myself talking you through it at this point. So the second day of 6.1 is obviously similar to the first day, but now we're going to have more than one region to find the area between. And these regions are broken up by points of intersection, and at those points of intersection, what you'll see is that the top and the bottom equations change roles. Okay, so for the warm-up though, it's just from what we did yesterday. Again, it's always important to get the graph to see a clear picture of exactly what we are trying to find the area of. This helps us visualize what's above and what's below. The interval for this started at 1, therefore this point of intersection is irrelevant for our problem. We can see here that the blue parabola is above the exponential between 1 and 5, the end of the interval. Okay, so going back to our notes here, let me get a sketch in front of us. I misspoke before, 1 and 4, not 1 and 5. So our parabola, I am sketching in blue to be consistent with what we had. Our exponential, sketched in red here. Okay. All right, take 2, more accurate sketch. Good. So now between 1 and 4, the given interval, blue is on top of red, or x squared is on top of e to the negative x. And we'll be able to set up our integral. Okay, so this gets put into the calculator, and we'll get our exact area. Remember, in Desmos, you get your integral symbol, you can type everything in, use your parentheses correctly, and end it with a dx. So 20.65 is the area between those two curves from 1 until 4. All right, so for today, steps are really similar, right? We're still going to have to get the picture, so we have to graph the function. Sometimes there's more than 2. We find those points of intersection. Calculator definitely can help here. And then we separate the region based on those intersection points. And finally, we integrate to find the area. So we will be creating adjacent integrals and adding their answers together. Again, the key is separate those regions. Now, if the graph's given, it helps us out a lot. We can see that there are 2 clear regions in this example. We have the pink or red parabola here, x squared minus 5x minus 7, and we have a blue line of x minus 12. Both of them are graphed, and we have the interval from -2 until 5. So inside of that interval, we can see that we have a point of intersection at 1. This is splitting our interval into 2 separate regions. For now, it's just the x-coordinate of these points of intersection that matter. Okay, so oftentimes we'll label these regions just for organizational purposes. Again, in each region, we are identifying the top function and the bottom function, and then setting up 2 separate integrals. If you recall back in the beginning of chapter 5 when we did our properties of integrals, we saw this property. We saw what was called adjacent integrals. Okay, and I'll explain that again in a little bit. So our first area, region A, goes from -2 until the point of intersection 1. The pink parabola is above the blue line, so we have x squared minus 5x minus 7 minus the quantity x minus 12. Plus, region B, the second space, goes from 1 until 5. There's no break in this graph, right? There's no break in this integral. We end with 1 in region A and we pick up again with 1 in region B. But now the line is above the parabola. So we have x minus 12 minus x squared minus 5x minus 7. Okay, and again, this is equivalent to the entire space from -2 until 5, like I was saying. We took one space and we broke it up into two adjacent integrals. Okay. Up to you. You can simplify or you can plug into the calculator as is. If you're going to plug in as is, just be cautious of your parentheses. You do have double sets in these, and they are important. Otherwise, go ahead and simplify here. Okay, so it simplifies -2 to 1, x squared minus 6x plus 5 dx, plus, from 1 to 5, -x squared plus 6x minus 5 dx. We'll take both of those integrals to Desmos or your graphing calculator and calculate their areas separately and add the answers together. Okay, so the first area is 27. Go back and do the second one now. Ten and 2/3. So our final answer is the sum of 27 and 10 and 2/3. So we get 37 and 2/3, or 37.67. Okay, here's another one. I want you all to give this a try. All right, the graph is given. The difference here is that we are not told the interval. Instead, we are told to find the area between the area in the enclosed space. So that would imply that we're using all 3 points of intersection, and the 3 points are breaking up the two separate integrals. Okay, be cautious when you're identifying which curve is which. In this case, it's easier because we have an x cubed and we have a linear. But sometimes you'll have two x cubes and you have to figure out, well, which one is which. The graphing calculator can help you, the order in which you type it in. Sometimes the labeling is not totally clear, so you have to look for different clues. Okay, so I'm going to stop talking here. I will quietly do the work, but try it on your own. Pause the video if you'd like, and then take a peek at the end. So notice with these integrals, they're quite similar, and in this case they actually are perfectly symmetrical. You might have predicted that when you saw the integral simplify. Even looking at the graph, the spaces look the same, and they are. The way the line bisects it through the origin, and two symmetrical points of intersection of -4 and 4. Not always going to be the case. Okay, so looking ahead, we just have a few more to do. This one has three equations, right? 8 over x squared, 8x, and x. So we're going to find the space that is bounded by all three of those graphs. Clear out Desmos and graph all three of them here. Okay. Color coding is so great about Desmos, right? We can clearly see we have three different functions there: the purple, the black, and the green. I'm just making sure that, there's no interval given, so it is region bounded by the graphs. That's important. Okay. So now we can see that triangular shape there, right? 0, 0, 2, 2 is the furthest bound, and 1, 8. Desmos won't allow you to have all three of those points highlighted at the same time, but what's important to note is the total interval goes from 0 to 2, and the middle intersecting point's at 1. Okay. So between 0 and 1, the top is purple, the bottom is black, and from 1 to 2, the top is green, the bottom is black. No other enclosed spaces, so we know for sure that this is the right area to find the area of. So I'm going to get a rough sketch here just so we have it for reference points. So the 8 over x squared, the x, and the 8x. Both x and 8x go through the origin. The 8x is now in red, it's steeper, and the x is in blue. And there's that little triangular shape that we're looking for. Remember, 0, 1, and 2 are the three x values that mean something to us right now. So even though this appears to be one region, which it is, right, it's one shape, there's still a place to break it apart because we need to be able to clearly define top over bottom. And at that point of intersection of x equals 1, the top functions change roles. Right, on the left side, the top is the purple line. On the right side of 1, the top is the green line. So that's how we're going to break up our two adjacent integrals here. From 0 to 1, red 8x minus blue x dx plus 1 to 2, green over blue, so 8 over x squared minus x dx. Okay, simplify it when you can, if you want to. Again, you don't have to. 8x minus x simplifies nicely. And then we're going to type them into Desmos. Okay, so first base is 3.5. Second space is 2.5. Can you look at my phone and bring it to me? Okay, so our total answer here is 6. Alright, next one. We have 3 lines. We have 8 minus 3x. Last two. 8 minus 3x, 6 minus x, and the horizontal line of y equals 2. So 8 minus 3x goes through the y-intercept of 8 and has a steep slope of -3. 6, that's supposed to be 6 minus x. I'm going to correct it in a second. And y equals 2 horizontal line. Okay, so all the graphs are adjusted and correct now. We can see that triangular shape. We can see that we have 3 important points of intersection here. But that triangular shape bounded from 1. Next point of intersection is at 2. And our end point is at 4. So those are the 3 important x values, 1, 2, and 4. From 1 until 2, we have purple above green, and from 2 until 4, we have purple above black. Okay, so we're going to get a sketch here. Right, and again, the lines are going to look similar. Their y-intercepts are slightly different, 8 and 6, but their slopes are also different, right? A -3 slope and a -1 slope. So the steepness will help us determine which one is which. Okay, so now on my graph here, I'm showing the 2 separate spaces from 1 until 2. In my color scheme, I have blue above green, and then 2 until 4, blue above black. So I'll write that in integral notation now. The integral from 1 to 2. Right, the blue is the less steep line, so that's the 6 minus x line, minus the green, 8 minus 3x. And then the second integral is going to go from 2 until 4. And now we have blue above black here. So 6 minus x minus 2. Simplify them, In this case, I would recommend it. It's not too difficult. 6 minus 8 gives us negative 2. Negative x minus negative 3x gives us 2x. And the second one goes to 4 minus x. So taking it to Desmos, plugging it in, and finalizing our answer. Okay, first integral equals 1. Also, guys, keep in mind that when these come out as triangles, you could find the area of the triangle, right? You'd have to find the height. This is not a right triangle, so be cautious of that. And the base. And you could use 1/2 base height when applicable. It's not always going to happen, of course, so I wouldn't depend on that. But area bounded by graphs sometimes is as simple as geometry. And in this case, it could have been. 1 plus 2 gives us 3. So we have one more example to cover. All right, so now we have our last problem of the day, 3 equations again. The difference here is that they're in standard form rather than y equals. Desmos, I believe, graphs in standard form, or you could just change them, right? Solve for y. So y equals negative x plus 4, y equals x, and y equals negative 3x plus 4. Okay. So I'm going to get the pictures of each of these 3 graphs. Again, they're linear, so we're going to be creating a triangular space again. The 3 x coordinates that are meaningful to us right now are 0, 1, and 2. Okay, so coming back to this screen, getting a rough sketch of it. Again, in order to distinguish between red and green, think about the slopes, think about the steepness of the slopes. Our first space goes from 0 until 1. Red is above green. Red is less steep than green, so negative x plus 4 minus quantity negative 3x plus 4. Dx. Second one goes from 1 until 2. Red is above black now. So negative x plus 4 minus x. Simplify, and then go ahead and put it into Desmos. first space gives us an area of 1. Second space is also 1. Our total area equaling 2. All right, so that is the end of today's lesson. Okay, there's one more day's worth of notes for this section. The way we're going to be structuring the next several weeks ahead of us, chapter 6 at least, we have 3 sections in chapter 6. Each of the sections will take 3 days to teach. The 4th day will be a practice day, and the 5th day will be a quiz day. So it'll be very, very structured that way. So it will take us a total of 15 E-days in our case to complete chapter 6. Okay. Plan after that. I'll reveal it as we keep moving, but also no final. There'll just be projects after that. So we may or may not cover one more topic. We might just go into our projects after chapter 6. I hope that helps. I did post the worksheet for this section 6.1, but it is not actually due until next Tuesday's block day, I believe. All right. Take care, guys. Hopefully the sound works this time.